No real surprise in the first one, right? V is equal to IR, also known as Ohm's law. What kind of circuit do resistors have the same power? Also known as series, right? There's actually three choices. There's parallel and series and the one we haven't talked about. Yeah, there are circuits that are neither series nor parallel. We're not going to get into those. You could imagine making up a problem identical to this, but phrased somehow to emphasize the idea of parallel circuits, parallel resistors. Could you write that question yourself?
But wouldn't you need to know, because it splits up, right? Would you like evenly split up?
Some kind of question to emphasize that particular property of, what is the property that parallel resistors have? They have the same voltage. So how might you write a similar but different question to number one, emphasizing the property about parallel resistors?
They have different currents. You would ask for the current and provide the voltage.
I would ask for the current and provide the voltage. Sort of similar but different, emphasizing the parallel structure. All right. Three resistors walked into a bar. No, three resistors determine the current for each that they have the same power. Yeah, three resistors walk into a bar. What did they have to drink? It's a good thing the semester didn't start off that way. So, power question. What is power? Any surprises for the power question? Other things to think about with power. V squared over R or IV. So one could imagine a similar but different question phrase using either of those other two relationships. Okay, and a bit of a voltage for each of those. You're saying this is way too easy, right? But you like it anyway. No.
I can't even.
So yeah, one of the reasons for really bringing in capacitors is so I can use all those prefixes. All right. All right, we'll move forward. Any surprise questions on any of these? Good. We are going to move forward. Question?
Am I counting the V2? Am I getting the answer? I have V2, but yeah.
Picofarad.
You have 8.14.
Pico, 10 to the minus 12.
Negative 10 to 6. Yeah.
Yeah, that would be a large number.
That's what might be the logic.
Right.
1, 2, 3, 4, 5, 6, 7, 8, 9. Huge.
Thinks we have a question here. For a capacitor, charge is blank voltage. For a capacitor, charge is blank voltage. Sounds nasty, doesn't it? What goes in the blank? Charges. Charge is stored voltage. Yeah, almost is. That's not what I was looking for. I'm looking for a relationship between charge and voltage. Is it proportional? Is charge proportional to voltage? So what is that capacitor formula that I gave you? C is equal to Q over V. So what I'm going to need to do is rearrange my symbols so I have Q something V, right? So I would say that Q is equal to CV. Are those proportional or inversely proportional? They are proportional, yes. Couldn't trick you there. And you might imagine some kind of question having to do with resistors. For resistors, current is blank voltage. Current is blank voltage.
Inversely.
Inversely proportional? For resistors, what does Ohm's law say? V is equal to I R. V goes up, I goes up, V goes down, I goes down. Those are proportional. So our symbol for a magnetic field is B. I need a few more symbols. A symbol for going into the page. You're thinking, what kind of symbol is this? Into the page. If I want to make something that's going into the page, like a direction. I mean, we have left, right, up, down, all that good stuff. How do we do into and out of? It's Z, but we need a way to symbolize this. Yeah, it is Z, but it's on the, how do we symbolize that on a paper? An X is actually it. Yes, this is going into the page. You can think of that as the tail feathers of an arrow. How about out of the page?
A point?
You're the point of the arrow. You got it. Not very imaginative. So when you see these symbols show up, that one means into the page, and this one means coming out of the page. And so now this one looking altogether different. This is a wire. That's a wire with a current I. how is that possibly a wire? Yeah. So the wire, you're looking down the axis of the wire. And the only question is, which way is the current going? And, well, we haven't said that's the wire. Now we'll decide to we're going to say that the current is going into the page. So that looks like it's not a point, but it actually is a point. That means it's a wire with the current going into the page. How about that? Could be worse, right? All right. So I've got a wire, and the current is slowing down the wire. It's going into the page. And why am I doing all of this? Because what is a current? Thinking about the current, what is a current? Moving charge? Moving charge. And moving charge creates magnetic fields, which is why all of this is coming up. And so this wire creates a magnetic field. And our question, the question we're trying to get at is, what direction is the magnetic field? And in order to answer that question, we have to know what direction the current is. So you're all happy with the current going into the page. All right. Take your right hand and imagine that your thumb is pointing in the direction of the current. And wrap your fingers around the wire. So if you have a pencil or something, thumb is going into the page. And you're looking at your fingers and the way that your fingers curl around the wire. And you want to write that down. How do they curl? They curl like so. They're going around like that, are they not? And so that is the direction of our magnetic field. It is circles around the wire. Concentric, meaning having the same center. The magnetic field makes concentric circles around the wire. So there's our current. I'm just going to draw another picture of it. About this point, you're liking this chapter. Just drawing circles. All right. Now, with that in mind, we're going to walk around to the other side of the wire. Actually, the wire starts filling in like that. What I want to do is have the wire going along the page. So now, let me get rid of that. Okay. Now that looks like a wire. That looks like a current. And now I need to figure out what direction the magnetic field is. I know it makes concentric circles around the wire, but how do I draw it? So you might want to visualize your thumb in the direction of the current. And if your thumb is in the direction of the current, your hand would have to wrap around it, right? So, let's hold something like that. Your fingers are coming out on top. And if your fingers are able to curl all the way around, they would hit the paper. Where your fingers hit the paper, you draw the X. That's an easy way to think about it. So here we put an X, and here we put a dot. And this is B, the magnetic field of the wire. questions? All right. Well, in this case, we've got directions. We've got our magnetic field coming out on the top, going on the bottom, the wires going along there. Right. Now we've got a wire loop, so I bent my wire into a circle, and I have a current going in it, and I need to figure out the magnetic field. And so just pick any section of wire you like, wherever is convenient. Pick, say, this section of wire here. And just do like you did before, figure out the magnetic field inside the loop and outside the loop. So if you were visualizing this section of wire, you would say that the magnetic field is coming out on the inside of the loop and going in on the outside of the loop.
Oh, no, there's something you said right.
Yes, it's the right-hand rule. Right-hand rule. Now, pick a different section of the loop and see if it changes. It's good. It keeps you flexible. You get within your proportional. Down here. Works. Notice that it comes out the same. Yeah, those of you that are actually left-handed, you got the advantage, because most of us are right-handed, and you know, just as one gets excited about writing answers down on a test, one forgets to put down their pencil, and one just uses that other hand and forgets it's the left hand. I've done that. So yeah, right-hand rule tells us the direction. Okay, for our next visual challenge, we need to rotate the loop so that we can look at it on edge. Turn that loop so that it's on its edge. Side view of a loop. And I'm going to, let's see, I want to have the current I is going in on the bottom. This time that's the current, and the current is coming out on the top. So we've rotated the loop such that the current is going in, goes around, comes back out, goes back down. Visual challenges. What direction is the magnetic field? It's that way, right? Which way? Well, just have your thumb go in the direction of the current on the bottom. So your thumb hits the paper and your fingers curl around. So if I do that, I visualize my fingers curling around that thing like so, right? Thumb in the direction of the current, fingers curl around. So there's my magnetic field, and if I do it on the top, I get to have my thumb coming out of the page, this time representing the current, and my fingers also curl around. Doing okay with that? And we're going to add in a few more lines. And let's see, converging and diverging magnetic field lines. They diverge here. They converge here. We talked about converging and diverging magnetic field lines in relationship to north and south poles. Where they diverge, it is what we actually call a north magnetic pole. And where they converge is what we call a south magnetic pole. So our current loop looks like a magnet. Oh, come on. Right? And yes, we use current loops to make magnets all the time. Run a current through a wire and you'll get a magnet. Questions on any part of that drawing? All right, here's the next visual challenge. It's a whole band of visual challenges. I want a whole bunch of loops, all right next to each other. Just line them up, a whole bunch of loops. These are current loops. So the current is going to be able to the same way it's going in on the top, it'll come in on the bottom and coming out on the top. So these are all the currents. A whole bunch of stacked up loops. Physicists need to get out more often. Stack up a whole bunch of current loops. How exciting is that? And we need to come up with the magnetic field. Pick any current loop. Pick any part of it. And it would look a whole lot similar to the one we just did, because I sort of set it up so it looks kind of like that. And if I sort of focused on this one here, I would say this one, at least right there, has a magnetic field going that way. And it turns out that they all add up, and they're all going the same way on the inside. The top and the bottom. And so here is our magnetic field. And this device creates a very nice uniform magnetic field. And this device is called a solenoid. And when we put a current in a solenoid, we get a magnetic field. And solenoids come into play through just an enormous number of things. Electromechanical switches. Your washing machine, wherever you use your washing machine. You throw the clothes in there, hit go, and it does its thing, right? And it opens a valve of water and lets the water in, then it shuts it off at the right time and gets rid of the water when it needs to, right? All those switches, all those valves are being operated by a solenoid. Different little solenoids doing different things. You put a current in it, and then you get a magnetic field, and then you can move something like an iron bar, and push it in or pull it out, depending on what you want to do with it. And you get your mechanical action by the presence or absence of an electrical current. Doorbells also have a nice little solenoid-like thing. Put a current in it, then it moves the ringer towards the bell, and then the spring pulls it back, so you get your doorbell sound. So these come up in all kinds of places. Very, very useful.
So the solenoid's just a wire.
Yeah, it's just a big loop of wire. All right. We are not done with our visual challenges yet. Next, our next biggest challenge in the visual challenging world is to go back and, okay, now I've got a solenoid. It's a solenoid. You're looking down the barrel of the solenoid. Ah, right. And it has a current. I. And what is the direction of the magnetic field inside the solenoid? It is coming out of the page, exactly. So we would indicate that like so. There's the magnetic field created by the solenoid. The fact that it's a whole bunch of loops stacked up together doesn't have any effect on it. Just treat it like a loop of wire. Okay, now this current, however, is getting stronger. The current is increasing. I might think of the current as a function of time doing something like that. So that's a graph of the current's behavior with time. It's increasing. Are we okay? What's happening to the magnetic field inside the solenoid? Well, if the current gets bigger, the magnetic field has to get bigger. Magnetic field is getting stronger, and what I've been struggling with is to come up with some symbol, some way to symbolize that. How can I make a picture of a magnetic field which is getting bigger with time? Bigger and stronger. Bigger, stronger, yes. So my approach to this is to do something like this. Start off with a small dot, and then I get a bigger dot, and a bigger dot, and a bigger dot. And I put a T underneath it. Right? Shows that time is increasing in that direction. The magnetic field is getting bigger and bigger with time. Seem like a reasonable symbol? In this current loop, I is decreasing. How would we indicate the changing magnetic field inside that current loop? Looking for a diagram of how do I indicate the magnetic field in this current loop. So there's two things. There's the direction of the magnetic field, into or out, and how it's changing with time. So attack the direction first. Still going into the page, yes? Okay, now how is it changing with time? If the current is decreasing, the current creates magnetic field, then the magnetic field must be decreasing with time. Yes, it's out of the page. Did I draw the other one wrong? No. Okay, good. So there's only 4 possibilities. You got 4 different coils there, each with different currents and changing in different ways. Counterclockwise and clockwise currents, increasing and decreasing currents. So draw all the magnetic fields for each one. What are the symbols we're going to use to indicate the magnetic field? Yeah, how's the magnetic field? And we're looking for the magnetic field inside the coil. And how is it changing with time, and some way of recording that information. And that's what you drew, right? Anyone having trouble with these pictures? Okay. There's only 4 possibilities, so there you go. We're not going to get wildly creative there. A blank creates a magnetic field. Current works. Actually, any current will create a magnetic field. Solenoid makes very useful magnetic fields, but any current will create a magnetic field. And what is it about a current that creates a magnetic field? Moving charge. You could use either phrase here, moving charge or current creates a magnetic field. Now, this is going to seem really bizarre, but if we change magnetic field and moving charge, we change places in the sentence, it would say something like this. Let me write it this way. All I did is we changed the word magnetic field and current. You're saying, well, wait a minute, how do we get physics out of grammar? And it doesn't work. But it was a fun idea. But it does work if we say a changing magnetic field. That was the only addition that we needed to put in there. A changing magnetic field creates a current. So if we have a current, we get a magnetic field. If we have a changing magnetic field, we get a current. All right, so here's where we take the big left turn today. We have a current loop. Actually, we don't have a current loop. That's a loop of wire, but it doesn't have a current by itself. But that wire is now in a changing magnetic field. So we have an external magnetic field that is increasing with time. And now, because I have this wire loop in this changing magnetic field, I expect to get a current in that loop of wire. So I guess I should really indicate what it is that creates that magnetic field. And we'll just imagine that there's another loop just outside it that is creating the magnetic field. So we'll say that here is our I, and that's increasing. This, however, is the current loop I'm interested in. So now I got two loops. One of them is our external loop that has a current that's increasing, creating that magnetic field. And the other is my smaller loop that I'm interested in. And I say that because that loop is in a changing magnetic field, I expect to get a current in it. I know it's terrible. All right. Here's the game. You're saying, what did I have for breakfast, right? The loop produces a current that produces a magnetic field that opposes the change in the external magnetic field. Hello. All right. So with these three dots here, you have to visualize that as the change in the magnetic field. And the magnetic field, the external magnetic field is getting bigger. How do you oppose something getting bigger? Well, you add more going in the other direction. So this is the magnetic field created by the current, by that smaller blue loop. It's opposing the thing. It's opposing the change. Yeah.
But technically, with the circle on the inside, should it be like on the outside, kind of, because you're making a current inside the line?
Inside of what?
I mean, like, because you have the loop, right? You said you had a change in magnetic field on the outside.
Yeah.
So would it, like, could you put X's on the outside instead of having two sets of circles on the inside?
Two sets of circles on the inside. So this red loop, this is the one that's with the changing current. And that's the one where the current is getting bigger, getting stronger and stronger magnetic fields. On the outside of it, yes, there is we could say that on the outside of it, the magnetic field is also getting stronger, going the other direction, right? That's just what is the thing that's producing the magnetic field that's changing. Now I have a wire loop in here that is experiencing the change in magnetic field, and this is known as Faraday's law. The loop responds in such a way as to oppose the change in the magnetic field. Okay, so I've got this loop of wire. This loop of wire is creating this magnetic field. This is going into the page. Which direction is its current? What direction of current produces a magnetic field going into the page? Clockwise or counterclockwise? Clockwise. So this thing is creating a current. We'll call that one I0, and I'll call this one I1. That current in that loop of wire is created to oppose that change in magnetic field.
We'll move it down.
Sure. And this little device that does that turns out to be incredibly important for three things: motors, generators, and transformers. And that's why I'm forcing you all to endure this stuff. Because, well, the generator is not part of the X-ray machine, but the motor and the transformer are. Your anode, the anode in your X-ray machine, it spins. So you have a motor, and that uses this idea. And the other really big thing, of course, is the transformer, which we will get to in a bit, probably not today. The transformer is the thing which takes us from 110 volts up to 110,000 volts, and we need this stuff. Okay, these are coils of wire. They just happen to be square instead of round. And these are unrelated to each other. These are external magnetic fields. We'll call that external. So I'm not caring how I created that external magnetic field. But somehow I create an external magnetic field and it has a coil of wire. And you can tell me what direction is the induced current in the coil of wire. So I'm bringing in this new term here, induced. When you see the word induced, it is a reference to Faraday's law. That coil of wire is responding to the change in magnetic field. What direction is the induced current? And your choices are clockwise, counterclockwise, or there is no current. You know, three choices there for each current. Clockwise, counterclockwise, or no current. No induced current. And the thing you want to, of course, look at is how do you oppose a decrease?
Is your question based on the B, or are you asking the opposing direction?
The answer is both.
Oh.
Because there's an external magnetic field which is changing. It's decreasing in time. How do you oppose a decrease? When your gas gauge in your car is going down and down and down, how do you oppose that decrease? You add more, right? So in this case, we're going to add more gas, more magnetic field here in the same direction. So this is the response. And in the other case, the response would be that. So all we're doing is looking at the change and figuring out what the response is. All right. Now that we know what direction the responding magnetic field is, all we need to know is what current gave rise to that response. What direction is the current that gave rise to that response? One's clockwise, one's counterclockwise. Which is which? So what direction would current have to flow in this loop to create a magnetic field that's coming out of the page? Counterclockwise. Okay, 3 more possibilities. See if you can draw them. Actually, 4 more possibilities. How would you do the same thing but make it slightly different? So similar but different, right? In the first 2 cases, they were decreasing in time. In the latter 2 cases, they are increasing with time. And again, we're looking for the induced current. So focus on the change in the magnetic field and figure out what you would have to do to oppose that change. How do you oppose that change? In these cases, it is increasing, and I need something that opposes an increase. When you want to oppose an increase, you add more going the other direction. So our response in this case will be like that, and our response in this case will be that. And so now we're looking for the currents. What current produces those responses? Let me scroll up really quick. Yes. Well, in this case, the response is coming out of the page. And to make a current, to make the magnetic field coming out of the page, similar to that, the response is going out of the page. All we need to have is current going in the counterclockwise direction, right? And of course, it's going to be opposite in the other one. Questions? I said there's two more possibilities. Can you imagine what they might be? Has something to do with choice C here. What would be a possibility that would produce no induced current? So what gives rise to that current? What is it that creates that current? Why is there a current there? Change in magnetic field. The induced current is a response to the changing magnetic field. So can you draw a situation where we have a non-changing magnetic field? Sure you can. In both cases, the external magnetic field is constant in time. One going in, one going out. And in both cases, we have no induced current. So there are all six possibilities there. So how are you going to see this on a test? That's what you really want to know. You don't care what all this stuff is, but you want to know how does it show up on a test? Or how could it show up on a test? Here's a coil of wire. There's a coil of wire with an induced current. Discuss the external magnetic field that must be present. me say, okay, I've got a coil of wire with induced current in it. The induced current is counterclockwise. Go to your 6 cases and see which out of your 6 cases produced a counterclockwise current. And then when you identify which of the 6 cases, write down what you can about those cases that produce that current. And what I like about this kind of question is that it requires 2 answers. So we have a counterclockwise current. It looks like in this case, number 2 and this one, number 3, give rise to that counterclockwise current. So we would say that the external magnetic field could be out of the page but decreasing, or into the page but increasing. Out of the page, what did we say? Out of the page, and we said out of the page, but decreasing. And there is my 2 responses. 2 possible situations which give rise to the same response. Questions? All right. Okay, I have an external circular loop with a decreasing current in it, and I have a smaller square loop of wire inside that. And the question is to discuss the induced current. If there is any. And that's your homework for Monday. No answers today. You get to share your own thoughts on that one. All right, that's it for today. Went through perhaps the most abstract part of this entire course, just all today. So if you survive today, the rest of it's not bad. Oh boy.